Steinhauer here, welcome back. Today's review question deals with the shapes of orbits. We've got 4 orbits here, and I'm curious which of these is physically realistic. Only one of these orbits is physically realistic. So take a look at them, pause the video, make a guess, and we'll come back and talk about each one of them in turn. Okay, so which of these is physically realistic? Well, let's take them one at a time. C, of course, is just ridiculous. There's no way that a planet would orbit in this figure 8 pattern. So C is right out. Let's not even talk about C. A, B, and D, however, are all physically realistic shapes, right? Orbits can be perfect circles and they can be ellipses. This is a perfect circle. These are ellipses. All of these are particularly good shapes for the orbits, but there's something about 2 of these that are off and are wrong. Let's talk about A first. A is a perfectly good elliptical orbit. The shape of this orbit is right, but there's something off about the sun's placement in this particular case. In this particular case, the sun will not be at the center of this particular ellipse because it has to be at one of the 2 focus points. And for this particular ellipse, the focal points will be something like there and something like there. So this is a realistic shape, but it would not be a realistic orbit because the sun would not be in this particular location for this particular orbit of this planet. D, similarly, this is a fine shape, but where would the sun be in this particular case? Well, in this particular case, the orbit is perfectly circular, and for a perfectly circular orbit, there is only one focus point, and that focus point is at the center. So if you are going to have a perfectly circular orbit, this is where you need the sun to be at the very center. And so the sun would be right there if this were the case. And the motion of the sun, of the planet around the sun, would be constant velocity at all times. B, that makes B therefore the realistic scenario. It has an elliptical orbit. The sun is indeed at one of the 2 focus points, and which is Kepler's first law. Kepler's second law is also exhibited here because the speed of this planet changes as it goes around the sun. In fact, it's fastest when it's closest to the sun and slowest when it's further away from the sun. This is a physical representation of how fast the planet would actually be moving at various points in its orbit as it moves around. So that's a good way to visualize Kepler's second law, which says that whose implications are planets orbit fastest when they're close to the sun and slowest when they're further away from the sun. Okay, let's get on to today's topic. And today's topic is motion and how we define motion and how we understand motion and how it works. So we're going to take some definitions from physics. Don't get too intimidated. These are fairly simple things, and you have experience with them in your everyday life. So first, let's do some definitions. Let's define some terms. For instance, speed and velocity. Speed and velocity in our colloquial sense are used interchangeably. So if we say we're moving at a speed of 20 miles an hour or moving at a velocity of 20 miles an hour, we mean the same things. They mean slightly different things in this class. Speed is simply the rate at which an object moves. So miles per hour, meters per second. It is some unit of distance divided by some unit of time. Velocity is that same thing, except that it also has a direction. So in physics, we would say 10 meters per second is a speed, 10 meters per second due east is a velocity. Or if you like, and you do like physics, velocity is a vector. It has both magnitude and direction. Speed is a scalar. It only has magnitude. It only has a value, 10, in this case, meters per second. Acceleration is a change in velocity. Anytime a velocity is changing, you have an acceleration. And so you have a unit of speed divided by time. So it's how much that velocity is changing as a function in a unit of time. And so there's another unit of time that comes up. And so the units of acceleration are meters per second or meters per second squared. or kilometers per hour, or kilometers per hour squared, or kilometer per hour per second. You can combine any distance unit with any time units you want to have an acceleration, although we'll usually be using units like meters per second squared. Okay, let's try to understand these and visualize and understand really why it's important to have a distinction between speed and velocity. So let's consider these three cars moving at different rates. And let's think about how speed and velocity and acceleration are different for the three of them. So let's start with car A. Obviously, its speed is increasing. In which direction does its, so let's just take a look at this quickly. It starts off at 30 kilometers per hour, and at the end, it's going 60 kilometers per hour, right? So it has increased in speed. It starts at 30, and it ends at 60. So let's talk about the velocity. In which direction is the velocity at the beginning? Well, it's moving at a certain, and I'm going to draw vectors to sort of represent this. It starts off moving to the right at a certain speed, and by the end, it's moving to the right at an even greater speed, right? The acceleration is how much this velocity has changed. And so the acceleration, you can think about it as the difference between these two vectors. The acceleration in this case also has to be to the right. It's accelerating in that direction because it's getting faster. It's moving in that direction faster. Okay, let's talk about C now. For car C, we start off going 60 kilometers per hour, and we end up with a stop sign going 0 kilometers per hour as we slow down. So again, at the beginning, what is the velocity? To start with, it's moving to the right at some speed. At the end, it's not moving at all. It's a vector that has 0 length, has 0 magnitude, and doesn't really point in any direction because the car has come to a complete stop. So, is there an acceleration here? The answer is yes, because the velocity has changed. Anytime you have a change in velocity, you have an acceleration. In this case, we usually refer to this as a deceleration in colloquial terms, but a deceleration is nothing more than an acceleration that points in the opposite direction. So again, the difference between these two vectors is the acceleration, and that in this particular case points to the left. So this is an example of the velocity being to the right, but the acceleration, the change in velocity, is to the left, and that's what causes the car to slow down and come to a stop at the stop sign. Okay, so it's going to be easy to mix these two up. It's going to be easy to misunderstand what velocity is and misunderstand what acceleration are. They can, in this case, do point in opposite directions. Sometimes they point in the same direction. That's an increase in speed. Here's a decrease in speed. That's a deceleration, or an acceleration that points in the opposite direction as your velocity. Okay, now let's take the example of B. In B, we are driving around in an arc, in a part of a circle. Our speed starts out at 60 kilometers per hour and ends at 60 kilometers per hour. Our speed is not changing as we make this turn. Is our velocity changing? The answer is yes. Our velocity is changing because the direction is changing, and velocity is both the speed and the direction. So if we had a velocity at the beginning of this arc, it would be in this direction. And if we have velocity at the end of this arc, it's going to be in this direction. And so again, our velocity at the beginning is like this, and our velocity at the end is like this. Is there an acceleration by car B? Is car B accelerating? It's not changing in speed, but an acceleration happens anytime a velocity changes. And since the velocity of car B is changing, there must be a non-zero acceleration for car B as well. This is somewhat easy to understand from your everyday motions. Imagine, put yourself in car A, right? you are starting off and you're pressing on the accelerator and you're speeding up. You are going to feel yourself pressed backwards into the seat of your car, right? That indicates that your acceleration is in the forward direction. Your feeling yourself pushed backwards is an indication of which direction the car is accelerating in the opposite direction that you feel yourself pressed back, that you feel yourself moved in the car as you're in it, right? In this example, in car C, you put on the brake to come to a stop, you feel yourself push forward in your seat. Therefore, your acceleration must be in the opposite direction. Well, put yourself in this car. In what direction will you feel yourself pulled as you make this turn? You should, at this point of the turn, feel a force pushing you towards the door of the car if you're driving the car and you're on the left-hand side, right? And so, therefore, it must be that the acceleration points in the opposite direction. The acceleration in this case, the average acceleration anyway, as the car makes this turn, must be in the down direction. And you can understand that from these vectors as well. Our vector starts off with an up slope and it ends with a down slope. The difference between these two vectors is a vector that goes straight down, and that must be the direction that the acceleration is actually moving in. Okay, that's a lot to start with. That's the basics of velocity and acceleration and speed. We'll come back and talk about gravity in the next video.